This video introduces a verification tool called KupC. KupC is designed for verifying the correctness of C program's dynamic software updating. You can download it from GitHub. Now, we will briefly demo its implementations and how to use it. First, let's have a look at its implementation. KupC is based on a rewrite-based executable framework K. If you want to learn more about K, please visit its official site. KupC consists of two parts. One part is the K definition of C languages operational semantics. It's called KCC, which is developed by the K group. We need to extend KCC to support some special annotations in C programs for updating. The other part is the definition of an updating mechanism based on KCC. In our case, we formalize a dynamic updating tool called Qian. It's formalized in this document. For example, we use this file to construct the updating restriction information. And this file uses restriction information to do the updating during the execution. In total, we defined around 300 rules to formalize the updating mechanism. Then, the two parts are compiled in K framework. Hence, we generate the executable tool KupC. Next, we show three different verification approaches of KupC. We can use them to perform formal analysis on the correctness of dynamic updating for different purposes. Let's see the first one. Here, we use KupC to simulate a dynamic updating. We use a shortest path program as a concrete example. We want to dynamically updating it. First, we need to annotate the original program to make it updatable. Keyword in update point is used to specify the range of the transaction. In that range, every statement must be in the same version. Two update points are inserted in the function for finding the shortest path. We call this function twice. The result of the two function calls should be same before updating. Next, we compile the original C program and the patch file together to generate executable and updatable code. In the command used for compilation, Option D is used to keep the temporal files. Option S is to shorten the length of these files, and the output executable file is named as map. Here is some execution information, and the final configuration is saved here. We run it with option NON. NON is used to specify the corresponding compiled files. Here is the output, and it shows that the second result has been updated. The second approach is to explore all possible dynamic updatings by searching. Again, we use the previous shortest path example. We execute it with option upsearch. Then, KupC shows all possible executions. Each corresponds to an updating case. There are three solutions found for this program. It means that there are three possible dynamic updatings. The output includes the locations where the three updatings happen. The third approach is to verify temporal properties of dynamic updating using LTL model checking. Let's consider a traffic light control system, for example. In the old program, the ignored addition non-determinism make light EW never be 1. The traffic light would never turn to green. We fix this bug in the new program. Using KupC, we compile the old program with a patch file and generate an updatable program. We run it with the option up LTL MC to enable the LTL model checker. We introduce atomic property update to express updating status. We verify that updating must be applied. The result is true, meaning that the property has been satisfied. The second property we want to verify is that after updating, the light EW must be turned to green infinitely. We define it as the LTL formula and verify it using this command. The result is also true. This concludes the demonstration of KupC. Thank you for watching, and remember that you can download and try KupC from GitHub.